Welcome back to AP Human Geography. Let's go ahead and talk today about some map projections. Okay, so when we talk about projections, what we're going to do is we see here is like projecting a movie screen. Well, the same thing happens when we have to project the surface of the Earth. Again, so we're talking about the Earth. We're not talking about a flat Earth. We're talking about a sphere, the globe. So how do we take that globe and then project it onto a flat surface? Well, when we see that, that is the scientific method of transferring this location on Earth's surface to a flat map is called the projection. So when we see this, we're going to see this, we're going to see many different variations of map projections that we're going to talk about today and kind of hone in on some of the main ones. There's many different ones that we'll talk about, but these are the main ones that we'll see throughout the year. And you've probably seen many of these and maybe even more. So the problems that will occur is what problem are you going to run into when you have to make a flat map out of this obloid spheroid? So we're talking about the sphere of the Earth. What problem do we run into? Well, the problem you're going to run into is distortion. All right, so we're going to run into distortion. There's going to be some type of distortion that is going to occur that is going to be problematic. We're going to distort a couple different things. It's going to be size, shape, distance, or direction. All right, so are we going to distort the size, the shape, the distance, or direction? So the four things that we can distort are size, shape, distance, direction. All right. Some people say that it's sad when you distort things. All right. Sad would be shape. Another way to say size would be area, distance, and direction, SADD. So distortion, we can talk about it several different ways: size, shape, distance, and direction. Or if you refer to size as area, then you can talk about it is sad when we have distortion, shape, area, distance, and direction. So when we talk about these, some of the main types of projection. Here's your Mercator projection. All right, so the Mercator projection is going to be your standard projection that we used to use a lot of the times for navigational purposes. All right, so what you're going to notice here is the major type of distortion that we're going to find is the land area. All right, and the shape of the lands are going to be distorted. So what we see is the size. Another way to say size is the land area. So the size and the shape are distorted. So if I look at this and I see how things are there, what we're going to notice is the distance is going to be preserved because we try to keep it as true of a grid as we possibly can. And so when we keep it as this grid, you can see it. You're going to have great distance preserved for the most part, and direction is going to be great. So this is for navigational and nautical purposes. We would actually like this projection. But what you're also going to see is with this Mercator projection, you're going to notice some of the issues are, look at Greenland and Asia. All right, Greenland and Asia are going to be huge. All right, and look at Antarctica. All right, so what we're going to see is we're going to see massive amounts of distortion when it gets near the poles. All right, so that's what we'll talk about here. We're going to see massive amounts of distortion there, and that's what we'll get into with the Mercator projection. The moleweed projection, all right, not as oftenly used, but we're going to see this a lot. It's going to kind of look similar to another projection, but I'm going to show you something that is a little bit different here. With the moleweed projection, we're getting a little bit more oval shaped here. And when we look here, what we're going to see is area is going to take precedence. So your size and area is going to take precedence over the shape of a territory. So they want to try to make sure they kept your land masses. They want to make sure you kept your land masses as close to the size and area mass versus the actual shape of what it would look like. So what we have here as parts of distortion for moleweed are going to be the angle, all right, because now we're not going to be a perfect grid, but we're also going to see an issue with the shape. The shape of these continents and land masses will be different, while we will notice the size. All right, look at the size difference and how Greenland has gotten smaller here. Europe is smaller, but look at how much larger Africa has gotten, because as large of a continent as it is, it should be given its due diligence, and that's where we see a change in these projections. Another type of projection. This is one of the most commonly used one that you've seen, especially in your textbooks. All right, so the Robinson, we see a lot more than the moleweed, but you start to see a little bit of different distortion here. With the Robinson projection, We're going to see this because it's a lot prettier to show things across space. So what they really like here and how you can really identify it is you can start to see, all right, look at the round shape on the left side and the right side of it. Up at the top, you're going to have a flat top, a straight top, and a straight bottom. So that is your Robinson projection. And you can see how it differentiates from the moleweed and definitely differentiates from the Mercator. Now, what happens here is they try to fix a little bit of everything, but they also distorted a little bit of everything. So everything is distorted a little bit here. We're talking about the shape of the areas are going to be distorted. The area and the size are going to be distorted. The distance and direction will be distorted. But this is a very appealing. This is aesthetically pleasing. People like the way this one looks. So they like to use it a lot more often, especially in educational purposes like your textbook, or even if you look at maps up in the front of your classroom most of the time. Then we get into this azimuthal projection. All right. So when we look at this again, this is going to be using when we're talking about polar projection. All right. This azimuthal projection, we're looking down, essentially a bird's eye view. So you can think about looking down at it and you can see it. You're looking from above, looking down on things. This is the way it would look for an azimuthal. So if we look at the name of it, though, an azimuthal equidistant projection, we see distortion. All right. The bottom half of the globe is going to be distorted and some of it kind of lost. All right. The shapes are definitely going to be distorted. All right. Based on how they're angled out. The distance is definitely going to be tougher to gauge, especially the further you get from the center. It's going to preserve distance and direction at the center point, but after then, distance is definitely going to be lost there. So some of your issues with distortion here are definitely going to be the shape, but more importantly, the distance is going to change the further you get from that central point, looking down at this polar azimuthal projection. Here's one, this one's not as significant that we use in class a lot, but it's just a little weird one I like to always share with you guys just to keep you on your toes. All right, the Fuller projection. All right, so with this Fuller projection, we kind of see it's kind of cut up like you're just playing with a pair of scissors and just cutting up paper. That's kind of how this Fuller projection will look. But what they do, they will maintain accurate shape of locations and size for the most part. But man, forget direction. You would not want to use this if you were navigating. All right, no way you're going to use this. So you're definitely going to see a distortion when it comes to the direction. But you notice if you look at these masses, the size and the shape or the area definitely are going to play a much better role of staying more maintained to what they should be. So the Peters projection, what we're going to see, all right, this is this one is a little bit more socially acceptable. All right, so when we say socially acceptable here, we realize that what happens with the size of an area, they want to try to make sure that, because for in this case, size is going to make a big difference of how you look at an area as far as strength, or area. The size of an area is going to matter as far as you look at a location of power, points of power. Well, on our earlier Mercator projection, we talked about how the area and the shape were distorted, and it made Europe look a lot larger than it really is supposed to be. Where if you look at this one is trying to keep as accurate as possible the size or the area of the land masses. Now, the shapes are a little distorted for sure, but the size of it is going to be as true as possible, which means, look, Africa is much larger than we see Europe to be, and it's given that its due diligence here. And this is more socially acceptable because it's not as Eurocentric saying Europe is going to be much larger. We have to give them a little bit more degree of power and significance. So what we see here with their Peters projection is the land in South America and Africa is definitely going to be stretched out a little bit. Europe's going to stay a lot more compact, and you're going to see that's allowing us to understand the significance of the land masses, all right, the accurate size and accurate land area of these locations. Another one we see a lot of the time throughout the year, and this one you've seen in some of your readings maybe already, the good Homogeneous interrupted projection. All right, so this is a very common used one here, and they use it a lot of the time because it shows areas across space nice and easy, and it takes away just all the bodies, the parts of water you're worried about, and it focuses on land masses. So it's really good and often used to show data across space and across the globe or across different regions, but you'll see this interrupted projection. So what happens is the points on the map they're not going to be continuous. So distance is definitely going to be thrown out here. Even to a degree, direction, you're not going to go up and down where these are. This is definitely not how the Earth really looks, but this allows us to show data across space, and it allows us to preserve a little bit more of the size and the representation of the continents. So it takes into what Peter's projection was trying to show us and preserve the size and the area of land masses, especially the continents and what we're looking at here. But it's obviously going to be a little bit tougher to some of you that just want it nice and clear, and this one may bother some of you, but it really is helpful to show data across space. And so that's where you'll see this interrupted projection used many different times. So if you look at these and you start to think, ooh, which ones are these? And you have to start getting quizzed. This is where you're going to see. Yep, that's it. All right, so hopefully you've done your quiz questions and you've seen your answers with these, and you've seen which ones each of these are and as they represent. Again, make sure we study these notes and pay close attention. These are the main projections we'll see throughout the year, and we will see them throughout many different topics. Thank you for joining us, and have a great day.